All right, everyone, we are back. Welcome back to Rocks for Jocks. I just got over a pretty rough case of COVID, and luckily we are now healed up, happy and healthy. My voice is back to normal, so we are ready to record some podcasts. Over the last few weeks, I've been going through one of Stephen Hawking's books, The Theory of Everything. It's a pretty short book, but it has a lot of information packed into it. Perhaps even better, it doesn't have too many of the big, complicated words which I normally associate with physics books. What I mean by there being a lot of information packed into it is that every couple of pages, and often every page, I've had to stop and take notes that help me understand the overarching ideas. The book itself only has around 170 pages and not that many words per page. So I looked it up online and saw that this book would hypothetically take someone less than 2 hours to read, but it took me a lot longer. I felt like every few pages had to be reread and reinterpreted until they sunk in. So over the next couple of episodes, I'm going to try to boil this book down to some of its most crucial information. As a result, I know it'll be impossible to catch everything, but hopefully the main ideas are clear enough that listeners learn something, and maybe even fun enough to inspire someone to pick up the book itself. The Theory of Everything by Stephen Hawking was released in the early 2000s, so I'm sure that most libraries have copies available, or you can probably find some pirated PDFs pretty easily online if you don't have good access to a library. The 7 lectures written about in this book by Hawking outline the following. Number 1, history of the universe. Number 2, combining Newton and Einstein's theories to show that the universe is very likely expanding. 3, showing how black holes are formed and talking about something called quantum uncertainty. Number 4 is about black holes and their energy leaks. Number 5 is about how space-time may have finite extent, but does not necessarily have any edges. 6 is why our past is so different from the future. Number 7 is searching for a unified theory, which allows for both quantum theories and other laws of physics. In the first lecture, Hawking discusses some important events from the history of our universe. The first was Aristotle showing that the Earth was round. The second was Ptolemy, who produced some reasonably accurate celestial models to show and predict the locations of planets and stars in the sky. If anybody's interested in a little bit more on these two researchers back from ancient times, I elaborated more on this topic in my episode called Coming of Age in the Milky Way. Next up is Nicholas Copernicus, who came up with the idea that the sun was the center of our planetary system, but he died before his ideas were taken really seriously. The next big researcher was Isaac Newton, who popularized the ideas of saying that gravity causes the moon to revolve around the Earth, while the Earth revolves around the sun. Newton's ideas specifically about gravity later on caused some confusion. Because if everything gets attracted to the center of the nearest large mass, that means the stars are going to be attracted towards the center of our universe, which was not in line with general thinking up until really recently. Most people until around the last 100 years thought that the universe was static. They thought that the universe was not expanding or contracting. And as I mentioned, Isaac Newton's theories of gravity meant that the universe would have to be contracting. Even in one of Einstein's equations, he added an extra constant value into his equation to force the universe to be static. He later famously referred to this as his greatest mistake because there wasn't actually any great evidence to assume that the universe was static. It was just the dominant way of thinking at the time. In 1929, Edwin Hubble showed that distant stars were moving further away, and this is including stars moving further away in every direction which we looked. This, combined with some of Hubble's other observations, meant that the universe was expanding, meaning that it must have all been at one location at one time, and it has expanded since then. Hubble also goes on to say that because everything came from one point, which is where the Big Bang happened, he said that anything which happened before the Big Bang could probably be ignored when trying to figure out what happens in our future. All right, I want to give my opinion on something here for a minute. These comments by Hubble were a pretty controversial view at the time, when Hubble was saying that nothing before the Big Bang mattered. Of course, one could say that studying what happened before the Big Bang is important if it tells us more about how the universe functions. But from my perspective, which I think Hawking was also going to touch on a little bit later in the book, it's pretty much impossible to get any information about what was going on before the Big Bang. Many scientists now consider the possibility that there wasn't really a version of time before the Big Bang. So what do I mean by that when I say that there wasn't really a version of time existing before the Big Bang? The best way I've heard this described, I think by the physicist Brian Greene, was that if someone asks you what's north of the North Pole, you might try to describe to them that the North Pole is as north as you can get. You might try explaining how to get further north from other locations. But the question, what's north of the North Pole, doesn't actually sound like a great question when we understand what the North Pole is. Or at the very least, that question doesn't have a very satisfying answer. So I think that asking what happened before the Big Bang may be the same type of question. There may not be a clear answer to what time and space we're doing before the Big Bang, and it may not matter as much to what is happening now in space-time. All right, back to the book. In lecture number 2, Hawking goes on to talk about how we know that the universe is expanding. He talks about some 20th century theories and combines them to what we previously knew about the universe. So in this chapter, Hawking begins with talking about some more detail on Edwin Hubble and his landmark discoveries in the early 1900s about how the universe is expanding. Hubble also uses telescopes to show stars beyond the Milky Way with a lot of empty space between them. Before this data was released publicly, most people thought that these stars were simply dimmer than stars in the Milky Way, and that's why it looked like there were fewer of them compared to the stars closer to us. Instead, Hubble was able to show that the stars were actually really far away using some of the star's own features. So I'm going to talk about this for a minute because I think this is a really interesting process that he used. For a little bit of background about starlight, we have waves of light that come from stars in slightly different wavelength patterns based on the type of star and the phase of life in which that star is in. From that pattern, we can then determine how bright the star is probably shining and call that the star's luminosity. We can then compare the star's luminosity with this level of light actually reaching our telescopes, known as its apparent brightness. So, if we have two stars which should have the same luminosity, meaning that they're shining the same amount, but one of those stars appears much brighter to us, that means the star appearing brighter to us is going to be closer. We can then repeat this process a bunch of times with stars in a single galaxy that we're observing. And if a bunch of those stars seem like they have reasonably close distance estimates to each other, meaning that they're all like similarly far away from us from the best measurements that we have, we are going to be happy to declare like a generally accepted distance to that galaxy from our own. Hawking later goes back to discussing theories of the universe contracting versus expanding versus being stuck in one place. If the universe were expanding slowly, gravity from all the stars and planets and dust would eventually cause the universe to stop expanding and start contracting. However, if the universe were expanding at a fast enough speed, then gravity wouldn't be strong enough to stop it. The researcher Alexander Friedman showed this mathematically and called it a, quote, critical rate, unquote. In 1922, prior to Edwin Hubble's findings, Alexander Friedman suggested mathematically what Hubble later found with his experiments, which is that expansion would be possible forever if the universe was moving at that critical rate. The critical rate is going to be proportional to the density of mass in our current universe. In other words, the more mass within the bounds of any section of space we look at, then the universe would have to be expanding even faster to counteract the additional gravity and continue putting off collapse of the universe forever. Okay, taking a breath and a pause after that. Alexander Friedman's work only even makes sense under the assumptions that the universe looks about the same in every direction, meaning that we have the same number of stars and galaxies in any direction that we look. Scientific evidence would later pop out that showed this assumption was pretty close to being true in every direction. This is clearly not true if we're looking at small to moderate scales. So for example, if we're looking at the Milky Way, things are not going to be perfectly even in every direction. We do not have the same number of stars in every direction. But if we zoom out and kind of looking at the large scale, this assumption does broadly hold true. So if we're looking at a bunch of galaxy clusters, say we're looking at like 1,000 galaxy clusters, there's going to be about the same number of them in each direction, about the same density in every direction. Ultimately, the forever expansion theory has been the leading theory for almost the last 100 years. If we add up all the visible matter in our universe and compare it with Friedman's calculations of how much matter is going to be needed to stop expansion of the current rate of our universe, we get to about 1% of the matter needed for gravity to fully stop expansion. If we include dark matter in those computations, which is matter only observed by its effects on gravity, we get to about 10% of the density needed. Hawking doesn't go deep into dark matter and its effects here, but I could definitely talk about that in another episode if people are interested. Another concept discussed in this section is about a survey of radio waves and the sources of those radio waves, which was studied in the 1950s and 60s at Cambridge. Strong radio waves were generally considered more recent than weak radio waves when they were looking out into space. So those researchers used this as a way to measure mass density at different points in times. In other words, if we see more frequent radio waves in this survey, that means that we have more matter seen per volume of space in that time period, meaning that we had a higher density of radio sources at that point in time. I'm oversimplifying, I think, quite a bit here, but basically these scientists found that the stronger, more recent radio waves were less frequent, leading to the conclusion that stuff is less dense now than it was in the past. This study was used as further evidence of an expanding universe theory. Lastly, in lecture number 2, Stephen Hawking talks about Roger Penrose, a researcher who later won the Nobel Prize. In 1965, Penrose showed that stars could collapse under their own gravity, eventually shrinking to a size of 0. And all that matter of the star is compressed into 0 volume, so the density of matter becomes infinite. This is now what we would call a black hole. Hawking himself was a PhD student at the time, who considered the possibility of reversing events in this change. He considered the idea of starting matter at size 0 and infinite density, then expanding it from there. Hawking eventually teamed up with Penrose to show that in an expanding universe, if following Alexander Friedman's assumptions of matter being approximately the same density in every direction, Hawking comes to the conclusion that all matter must have come from a single singularity of apparently size 0 and infinite density. Okay, I think this might be a good stopping point here. End of lecture number 2. If you enjoyed this podcast, let me know. If not, let me know too. Thank you all for listening to Rocks for Jocks.